Alrighty, this is Physics Lab 3, and this one's a little different from previous labs, because in the past we've been tasked with, looking at something and then creating a model to predict its motion. So we'll have stuff from t1 to tn, and we want to predict what'll happen at tn plus 1, or we want to compare our prediction to what actually happened at, like, t7. In this case, in this lab, we're not actually doing that. What we got was a bunch of data, a whole lot of data, and instead of like predicting at 1461 or like creating a model and comparing our 1416 to theirs, no, we want to infer something else about the universe. In this case, we want to figure out the mass of the black hole that this star is orbiting using math and using physics. And we can do that actually really accurately. My results were very good, accurate to like 5 significant digits. And we can do that very well, which is cool because it means we can like infer things about the world from things we can see, and that's kind of awesome. So yeah, this is the data file, and this is the code, and you don't need to really worry about this. So here's the important parts of the code. Skip some stuff. All right, so we get starting numbers here. These were given to us, and this is a day in seconds. Okay, so then we compute x and y velocities. We did this for y velocity as well, just using dx equals x2 minus x1, and then velocity of x equals dx over dt. Same thing for y. Okay, so v initial and v final are x. Basically, v initial is x, is the velocity at the previous second, and we make a vector of that, and then v final is the velocity at the current second or the current day. P is equal to mv. That's like super important to our physics class, right? It's like basic and of great power. So P initial and P final are calculated with that. Delta V and delta P, well, D of something is equal to something 2 minus something 1. So that's essentially what it is. V final and P final minus V initial and P initial, and that's how you get those. dP dt is just delta P over delta T. Okay, so then, and Fnet is kind of, it's the same thing, but not exactly. I'll get to that in a minute. So then you calculate the parallel and perpendicular components of the force, and then you get to this, and I'll get to that in a minute. And the reason you calculate the perpendicular and parallel components is for graphs. So this is what it looks like when you run it. You get these 3 vectors. Yellow vector is net force, and blue and black are perpendicular and parallel, respectively. You can see the force was big there, and now it's little again. Force is changing, right? That's super important. Okay. So that print statement at the end essentially was printing this. This is T, and this is that gigantic equation, mag F net times 1 point blah, 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 this thing. And what is this? This is, well, if you come over here, force equals gmm over r squared, where big M is mass of thing it's orbiting, and little m is mass of thing. And that's what you actually have over here is this second equation, which is just some algebraic shenanigans on the first one. So F divided by M divided by G times r squared is equal to big mass. And, well, if you come over here, F net times this, just ignore this, divided by star's mass, little m, divided by big G, times the radius of the kissing circle, because this is the star's position and this is the black hole's position, just vector of those two, times squared. So that's the same equation. And so that's how we calculate everything. It works, it's exact, it's really good. So, what does this all mean? Well, first question, how are Fnet and delta P over delta T different? And the same arguments apply to the other one, so I'm just going to talk about those two. And the answer is that for a constant force, they're the same. So for a constant force, Fnet is equal to dP over dt. However, and that's true on like very short time scales, or if you're just like pushing something across a table with a force of 8 newtons. However, for non-constant forces, which is what we had because you could see the arrows were changing and getting bigger, the net force on the object was changing as it moved, it's actually impulse, which is equal to delta P, so those are the same. Impulse is equal to the integral of the force times dt. On small time scales, we ignore the integral because they're the same, and we just get that it's equal to f dt. But for large time scales, when the force is changing, we can't do that, and so that's why they're different. So for the lab, we assume small time scales and just sort of say that it works, and it does. So then, what if we replaced the black hole we had with a different one, and all of our data stayed the same? Would the black hole be any different? Could we tell that the black hole was different? And the answer is the black hole wouldn't be any different, and here's why. Essentially, you have this equation, and you know that F m and r squared are going to be the same because the star data doesn't change, and all of this code, therefore, given the same input, will give the same output. So we'll get that f, m, and r squared are the same. And big G isn't going to change. Like, that's not going to happen. I'm not going to wake up tomorrow and be floating because the relationship between gravity and distance just suddenly became like a tenth of what it was. It's not going to happen. And 2 also isn't going to like magically change. So the resultant mass has to be the same because all of these numbers that you're putting into the equation are the same. And essentially that's the reason that it has to be the same black hole. So yeah, I think that's everything. Thanks for watching.